Welcome to Lesson 5 of my Red Pill course on calculus, where we will focus on the differential calculus. As we said in Lesson 1, differential calculus deals with the question of how to define and calculate the instantaneous rate of change of a variable quantity. In geometric terms, how to define and calculate the slope of a curve. In the physical example of an accelerating car, the question is how we can define and calculate the instantaneous velocity of the car at a specific point in time, or how we can define and calculate the slope of the curve at a given point in the position versus time graph. A straight line that touches the curve and has the same slope as the curve is called a tangent. Therefore, the question of the slope of a curve is also called the tangent problem. In physical situations, such as an accelerating car, the instantaneous rate of change of a quantity should be approximately equal to the average rate of change over a short time interval. Geometrically speaking, the slope of a curve at point x should be approximately equal to the secant slope over a short interval delta x, where the function values are taken at the 2 points x and x plus delta x. As we move from x to x plus delta x, the function value changes by delta y from f of x to f of x plus delta x. So the secant slope is the rise delta y over the run delta x, or f of x plus delta x minus f of x over delta x. In our Red Pill course, we can consider the secant slope over an infinitesimal interval, dx. The secant slope is then dy over dx, or f of x plus dx minus f of x over dx. dx and dy are called differentials. If f and x are standard, then the standard part of dy over dx is a reasonable candidate for the slope of the curve at x, the tangent slope at x. If we want to pursue this idea further, we must ensure that there is some non-zero infinitesimal dx such that x plus dx is in the domain of f, and that the standard part of dy over dx is the same for all such dx. This amounts to the following definition. Let D be a subset of R, f a function from D to R, x a member of D, and B a real number, all standard. If there is some non-zero infinitesimal dx such that x plus dx is in D, and for all such dx the differential quotient f of x plus dx minus f of x over dx is infinitely close to B, that is, B is equal to the standard part of the differential quotient, then we call B a derivative of f at x, and say that f is differentiable at x. If f is differentiable at x, the derivative of f at x is uniquely determined, and is denoted by f prime of x. The uniqueness follows from the fact that two standard numbers that are infinitely close must be equal. As usual, we can generalize our definition through standardization, a concept we introduced in Lesson 2 and have already applied in the cases of continuity and uniform continuity. We define the set deriv as the standard subset of f cross r, whose standard members are those that satisfy phi of fxb, where phi of fxb means fxb is standard, x is in the domain of f is differentiable at x, and b is the derivative of f at x. For general fxb, we call f differentiable at x and b a derivative of f at x if the triple fxb is a member of deriv. Since deriv is a standard set, we can conclude by transfer. If a function f is differentiable at point x, then the derivative at x is uniquely determined, and we denote it by f prime of x as in the standard case. More generally, an internal, that is, conventional parameter-dependent statement involving differentiability or derivatives is true for all parameter values if it is true for all standard values. This means when proving conventional theorems of differential calculus, we can therefore always prove the standard case first and then generalize it by transfer. As a first example, we prove that differentiability implies continuity, a concept we introduced in Lesson 3. For all real functions f and all x in the domain of f, if f is differentiable at x, then f is continuous at x. Let us first consider the standard case. So let fxb be standard and the triple fxb a member of deriv, which means that f prime of x is equal to b. Then for all non-zero infinitesimals dx, if x plus dx is in the domain of f, then the differential quotient is infinitely close to b, that is, equal to b plus epsilon for some infinitesimal epsilon. Hence, if we multiply by dx, f of x plus dx is equal to f of x plus b plus epsilon times dx. And this is infinitely close to f of x, because b plus epsilon is limited, and limited times infinitesimal is infinitesimal. This means that f is continuous at x. We have thus shown that for all standard fxb, if b is the derivative of f at x, then f is continuous at x. By transfer, this implication holds for all fxb. We say that a function f is differentiable if it is differentiable everywhere on its domain. In this case, we define the derivative function f prime from the domain of f to R, which maps x to the derivative of f at x. Here is a trivial example, the constant term rule. For all real numbers c, the constant function fc from R to R that maps x to c is differentiable, and fc prime is equal to f0, the constant zero function. Geometrically, this is clear because the graph of a constant function is a horizontal line, and a horizontal line has a slope of 0 everywhere. We will now prove this using the definition of the derivative. For any standard reals Cx and any non-zero infinitesimal dx, the differential quotient is equal to c minus c over dx, which is 0. Hence, for all standard reals Cx, the triple fc x0 is a member of deriv. Then, by transfer, this is true for all reals Cx. That is, fc prime of x is equal to 0. A few remarks on the designation of differentials. Let f be a real function and x in the domain of f, both standard. In the following proofs, we always assume that dx is a non-zero infinitesimal for which x plus dx is in the domain of f. We define the related quantity df as f of x plus dx minus f of x. Previously we wrote dy instead of df, but the designation df is more flexible if we want to consider the differentials for multiple functions. When computing derivatives, we will often use the equation f of x plus dx is equal to f of x plus df. If f is differentiable at x, and therefore also continuous at x, then df is infinitesimal and f prime of x is the standard part of the differential quotient, that is, the standard part of df over dx. We will now prove some differentiation rules. Let f and g be real functions and x a member of their common domain. If f and g are differentiable at x, then the sum rule tells us that their sum f plus g is differentiable at x and that the derivative of the sum is equal to the sum of the derivatives. The product rule is a little more complicated and tells us that the product fg is differentiable at x and the derivative is f prime of x times g of x plus f of x times g prime of x. If one of the two functions is constant, we obtain the following corollary from the product rule. The derivative of c times f is equal to c times the derivative of f. A constant factor c can be moved in front of the derivative. To prove the sum rule, we compute the differential quotient for the standard case. The numerator is f of x plus dx plus g of x plus dx minus the sum f of x plus g of x. We now use that f of x plus dx is equal to f of x plus df and g of x plus dx is equal to g of x plus dg. Then the summands f of x and g of x are cancelled out by the corresponding negative terms, leaving df over dx plus dg over dx. Since f and g are differentiable at x, the standard parts of each of these two summands exists, and the standard parts are the derivatives f prime of x and g prime of x. So taking the standard parts yields the desired equation f plus g prime of x is equal to f prime of x plus g prime of x. The general case follows by transfer. We proceed in the same way with the product rule and compute the differential quotient for the standard case. Here the numerator is f of x plus dx times g of x plus dx minus f of x times g of x. Again, we use f of x plus dx is equal to f of x plus df, and g of x plus dx is equal to g of x plus dg. We can multiply this out and obtain this fraction, where the term f of x times g of x and the corresponding negative term cancel each other out. We can group the remaining terms as follows: df over dx times g of x plus f of x times dg over dx plus df over dx times dg. Since f and g are differentiable at x, all terms are limited, so we can take their standard parts. Overall, this leads to fg prime of x is equal to f prime of x times g of x plus f of x times g prime of x plus f prime of x times 0, where 0 is the standard part of the infinitesimal dg. The last summand is 0 and can be omitted, and we obtain the desired equation. The general case follows by transfer. The next differentiation rule is the chain rule, which applies to the composition of two functions. Let f and g be real functions, x be in the domain of f, and the range of f be the domain of g. If f is differentiable at x and g is differentiable at f of x, then the composition g after f is differentiable at x and g after f prime of x is equal to g prime of f of x times f prime of x. In the proof, we use the differentials df, which, as usual, is equal to f of x plus dx minus f of x, and dg, which is defined as g of f of x plus df minus g of f of x, since g is differentiable at f of x. We consider the standard case and compute the numerator of the differential quotient. dg after f is equal to g of f of x plus dx minus g of f of x. This is equal to g of f of x plus df minus g of f of x, since we can replace f of x plus dx with f of x plus df again. This is equal to g of f of x plus dg minus g of f of x, since we can replace g of f of x plus df with g of f of x plus dg. These terms cancel each other out, leaving dg. If df is equal to 0, then dg after f is also equal to 0. This already follows from the second line, since the terms cancel each other out there. When we divide by dx and take the standard parts, we get f prime of x is equal to 0 and g after f prime of x is equal to 0, and hence the desired equality. If df is not equal to 0, then we have dg after f over dx is equal to dg over dx. And this is equal to dg over df times df over dx. Since f is differentiable at x and g is differentiable at f of x, both fractions are limited. Taking the standard parts yields the equation asserted by the chain rule. The general case follows by transfer. In a similar way, you can prove other differentiation rules such as the reciprocal rule or the inverse function rule. The power rule states that the function f, which maps x to the power of n, is differentiable and its derivative is n times x to the power of n minus 1. We can prove this using mathematical induction. For the base case, n equals 1, consider the differential quotient, which is equal to 1 regardless of x. For the induction step, apply the product rule to x to the n times x. As a corollary, we obtain any polynomial function is differentiable. We now come to an important theorem of differential calculus that helps determine local extrema of a differentiable function. Let f be a real function on the open interval from a to b, and let x0 be a member of this interval. If f is differentiable at x0 and has a local extremum at x0, then f prime of x0 is equal to 0. Note that the vanishing derivative is a necessary but not sufficient condition for a local extremum at x0. For the proof, let f and x0 be standard. Let f be differentiable at x0 and have a local maximum at x0. The case of a minimum is analogous. Then there exists a positive epsilon such that for all x in the open interval from x0 minus epsilon to x0 plus epsilon, f of x is less than or equal to f of x0. Then, by transfer, there exists a positive standard epsilon with this property. In particular, for any positive infinitesimal dx, f of x0 plus or minus dx is less than or equal to f of x0, and therefore this inequality holds. Why? Well, the numerator is less than or equal to 0 in both fractions. The denominator is positive in the left fraction and negative in the right fraction. Both fractions are differential quotients, one with the differential dx and one with the differential negative dx. Since f is differentiable at x0, we can take the standard parts and obtain f prime of x0 less than or equal to 0 less than or equal to f prime of x0. Hence, f prime of x0 is equal to 0. For general f x0, the assertion follows by transfer. As usual, from the interior extremum theorem follow Rolle's theorem, the mean value theorem of differential calculus, and that functions that are continuous on the closed interval from a to b and differentiable on the open interval from a to b with a vanishing derivative are constant. You can read about this in any conventional calculus textbook. Let's summarize the most important points from this lesson. The idea of an instantaneous rate of change, the slope of a curve, is expressed in infinitesimal calculus by the concept of the derivative. Differentials describe an infinitesimal change of a quantity. For differentiable standard functions, the derivative at standard points is the standard part of the differential quotient. The general case is covered by standardization, the standard set deriv. Conventional theorems involving differentiability and derivatives can be proven by proving a standard case and then using transfer. That's all for now on differentiation. I look forward to welcoming you to the next lesson on integration.